In the vast expanse of our solar system, a celestial dance unfolds around the ringed giant, Saturn. Among its many partners, one moon stands out, captivating our imagination with its enigmatic beauty and scientific allure. This is Dione, a world of ice and rock, locked in a gravitational embrace with its colossal planetary companion. Discovered in 1684 by Giovanni Domenico Cassini, Dione has since become a subject of intense scientific curiosity. As we delve deeper into the mysteries of Dione, we embark on a journey to understand not just a single moon, but the intricate workings of our solar system and the potential for life beyond Earth. One of the most striking features of Dione is its network of bright, wispy streaks that crisscross its surface, contrasting sharply with the darker, cratered terrain. These enigmatic lines, some stretching for hundreds of kilometers, are believed to be relatively young features, potentially formed by material ejected from recent impacts or by eruptions of icy material from Dione's interior. Adding to the mystery, Dione possesses a tenuous atmosphere, so thin that it's more accurately described as an exosphere. This extremely thin veil of gas, composed mainly of oxygen, is thought to be generated by the interaction of Saturn's powerful magnetic field with Dione's icy surface. The discovery of this tenuous atmosphere, along with evidence of past geological activity, has placed Dione among the growing list of celestial bodies in our solar system that may harbor the potential for life. Dione's story is intricately woven with the stories of its fellow moons in the Saturnian system. It is locked in a complex gravitational dance with two smaller moons, Helene and Polydeuces, which share Dione's orbit, residing at stable points known as Lagrange points. The gravitational interactions between Dione and its companions, as well as with Saturn itself, contribute to the moon's internal heating. This tidal heating may be responsible for Dione's past geological activity, including the potential formation of its subsurface ocean. As we unravel the mysteries of this icy world, we gain a deeper understanding of the processes that have shaped our solar system and the potential for life to arise in the most unexpected of places. Dione's surface, like a canvas painted with the strokes of cosmic history, tells a story of ancient impacts and geological processes. Its primarily icy composition, reflecting sunlight back into space, gives Dione its high albedo, a measure of its reflectivity. It is heavily cratered, a testament to the relentless bombardment of asteroids and comets that have shaped the solar system since its early days. Some of these craters are truly colossal, stretching over 100 kilometers in diameter, dwarfing entire cities on Earth. These features, such as the enigmatic bright streaks and evidence of past tectonic activity, suggest that Dione has experienced periods of internal heating and surface resurfacing, erasing some of the older impact craters and creating new features that continue to intrigue scientists. Among Dione's most striking and enigmatic features are the bright, wispy streaks that crisscross its surface, standing out in stark contrast against the darker, heavily cratered terrain. These linear features, some extending for hundreds of kilometers, have puzzled scientists since their discovery. One possibility is that these bright streaks are the result of material ejected from relatively recent impacts. Another intriguing possibility is that these streaks represent fractures in Dione's icy crust, through which material from the moon's interior may have erupted in the past. This possibility raises exciting questions about the potential for past or even present-day cryovolcanic activity on Dione. Dione's surface is a study in contrasts. a testament to the diverse forces that have shaped this icy world over billions of years. Alongside its heavily cratered regions, Dione also exhibits areas of smoother terrain, suggesting periods of resurfacing that erased older impact scars. Adding to this diversity, Dione displays evidence of tectonic activity, with long linear features known as chasmata or chasms cutting across its surface. These chasmata, some stretching for hundreds of kilometers, are thought to be the result of tectonic stresses within Dione's icy shell. These tectonic processes may have played a crucial role in the evolution of Dione's subsurface ocean, potentially providing pathways for the exchange of material and heat between the ocean and the surface. While Dione's surface is a captivating tapestry of ice and scars, it's what lies beneath that truly captures our imagination. Scientists believe that Dione, like its larger sibling moon Enceladus, harbors a global subsurface ocean of liquid water hidden beneath its icy shell. The evidence for Dione's subsurface ocean comes from a variety of sources. Gravitational measurements by the Cassini spacecraft suggest the presence of a layer of liquid water beneath Dione's icy surface. The presence of this subsurface ocean has profound implications for our understanding of Dione and its potential for harboring life. Dione, like the other moons of Saturn, is believed to have formed billions of years ago within a swirling disk of gas and dust that once encircled the young gas giant. This disk, known as a circumplanetary disk, was the birthplace of Saturn's magnificent ring system and its diverse family of moons. Dione's early formation was likely a chaotic and violent affair. The young moon, still hot from the energy released during its accretion, would have been subjected to a relentless bombardment of leftover planetesimals. As Dione cooled and solidified, its interior differentiated, with heavier elements sinking towards the center to form a rocky core, while lighter compounds, such as water ice, formed an outer shell. The bombardment of Dione didn't end with its early formation. Throughout its history, the Moon has continued to be impacted by asteroids and comets, albeit at a lower rate than during the early solar system. While impacts have played a significant role in shaping Dione's surface, they are not the only geological process at work. Scientists believe that Dione has also experienced periods of cryovolcanism, a type of volcanic activity where the erupted material is not molten rock, but rather ices, such as water ice, ammonia, or methane. These cryovolcanic eruptions, if confirmed, would have significant implications for our understanding of Dione's interior and its potential for harboring life. Dione's surface is etched with a network of linear features, including chasmata or chasms, that hint at a more dynamic and geologically active past than initially meets the eye. These chasmata, some of which stretch for hundreds of kilometers across Dione's surface, are thought to be the result of tectonic stresses within the Moon's icy shell. These tectonic forces, potentially driven by tidal interactions with Saturn and other moons, have caused Dione's icy surface to crack and shift, creating the chasmata we observe today. The presence of these features suggests that Dione's icy shell is not a static, monolithic structure, but rather a dynamic layer that has experienced significant deformation and reshaping throughout its history. These tectonic processes may have played a crucial role in the evolution of Dione's subsurface ocean. Beneath Dione's icy shell lies a hidden realm that has captured the imagination of scientists and space enthusiasts alike, a global subsurface ocean of liquid water. This ocean, inferred from gravitational measurements and the Moon's geological activity, is thought to be tens of kilometers deep, sandwiched between Dione's icy crust and its rocky core. Liquid water is considered essential for life as we know it, and its presence on Dione raises the tantalizing possibility that this icy moon could be home to extraterrestrial organisms. While much remains unknown about the conditions within Dione's ocean, scientists believe that it could be similar to the subsurface oceans of other icy moons, such as Europa and Enceladus. These oceans are thought to be salty and rich in dissolved minerals, potentially containing hydrothermal vents on their ocean floors. For centuries, Dione remained a distant, enigmatic world, its secrets hidden beneath a veil of ice and distance. That all changed with the arrival of NASA's Cassini spacecraft at Saturn in 2004. Cassini, a robotic emissary from Earth, revolutionized our understanding of the Saturnian system, and its close encounters with Dione proved particularly revelatory. Over its 13-year mission, Cassini performed multiple flybys of Dione, capturing stunning images of its surface in unprecedented detail. Equipped with a suite of sophisticated instruments, Cassini was able to probe beneath Dione's surface, providing insights into its internal structure and composition. One of Cassini's most significant discoveries at Dione was the mounting evidence for a subsurface ocean hidden beneath its icy shell. The spacecraft's gravity measurements, which detected subtle variations in Dione's gravitational field, suggested the presence of a layer of liquid water beneath its surface. These variations, while small, were consistent with a global ocean tens of kilometers deep, sandwiched between the moon's icy crust and its rocky core. Further support for a subsurface ocean came from Cassini's observations of Dione's surface features. The presence of tectonic features, such as chasmata, suggested that the moon's icy shell had experienced significant deformation and reshaping throughout its history. Such tectonic activity could be driven by tidal forces from Saturn, but the presence of a subsurface ocean would amplify these forces, making the icy shell more susceptible to cracking and shifting. The evidence for a subsurface ocean on Dione, while compelling, is still considered circumstantial. However, the combination of gravity measurements, tectonic features, and the moon's overall geological activity strongly suggests that Dione harbors a hidden realm of liquid water, making it a prime target in the search for life beyond Earth. Section 3. A dynamic duo, Dione and Enceladus compared. Dione's potential for harboring a subsurface ocean has drawn comparisons to its smaller, more famous sibling moon, Enceladus. Enceladus, a world of ice geysers and a confirmed subsurface ocean, has become a poster child for the search for life beyond Earth. While Dione's geological activity appears to be less pronounced than Enceladus's, the two moons share striking similarities that hint at a shared history and potential for habitability. Both Dione and Enceladus are thought to have formed in a similar manner, accreting from the disk of gas and dust that once surrounded Saturn. Both moons are primarily composed of water ice, and both exhibit evidence of past and present-day geological activity, suggesting the presence of internal heat sources. This internal heat, likely generated by tidal forces from Saturn, is thought to be responsible for maintaining their subsurface oceans. The similarities between Dione and Enceladus suggest that the conditions necessary for life may be relatively common in the outer solar system, particularly among icy moons orbiting gas giants. These moons, once thought to be cold, dead worlds, are now recognized as potential havens for life, harboring vast hidden oceans that could be teeming with microbial life. Section 4. The Oxygen Enigma, a Thin Atmosphere's Tale. While Dione's surface is too cold and airless to support life as we know it, the Moon does possess a tenuous atmosphere, more accurately described as an exosphere. This exosphere, while incredibly thin, is composed mainly of molecular oxygen, a surprising finding that has sparked intrigue among scientists. The oxygen in Dione's exosphere is thought to be generated by the interaction of Saturn's powerful magnetic field with the Moon's icy surface. As charged particles from Saturn's magnetosphere bombard Dione's surface, they can split water molecules in the ice, releasing oxygen atoms that can then combine to form molecular oxygen. While the amount of oxygen in Dione's exosphere is far too low to support life as we know it, its presence raises intriguing questions about the potential for more complex organic molecules to exist on the Moon, particularly in its subsurface ocean. Oxygen, a highly reactive element, can play a crucial role in biological processes, and its presence in Dione's exosphere hints at a more chemically complex world than initially meets the eye. Dione, a key player in Saturn's moon system, dances in a complex gravitational ballet. Saturn's gravity sets the tempo, orchestrating this celestial dance. Dione's orbit and geology are shaped by these gravitational forces. Tidal forces within Dione generate internal heating, driving geological activity. Among Dione's dance partners, Helene stands out as its closest companion. This smaller moon, named after a mythical Greek heroine, shares Dione's orbit, residing at a stable point known as the leading Lagrange point. Imagine this Lagrange point as a gravitational sweet spot, where the gravitational pull of Dione and Saturn balance perfectly, allowing Helene to maintain a fixed position relative to its larger sibling. This orbital configuration, known as a Trojan relationship, is a testament to the elegant workings of celestial mechanics. Helene, trapped in Dione's gravitational embrace, perpetually leads its larger companion in their shared orbit around Saturn. This gravitational tango, however, is not a one-sided affair. Helene's presence, though small, exerts its own subtle influence on Dione, contributing to the intricate web of gravitational interactions that shape the Moon's long-term evolution. As Dione and Helene waltz around Saturn, their gravitational interplay can subtly alter their orbital paths over vast timescales. These orbital perturbations, while seemingly insignificant in the short term, can accumulate over millions of years, potentially influencing the long-term stability of their orbital resonance. Understanding these subtle gravitational interactions is crucial for unraveling the dynamical history of Saturn's moon system and predicting its future evolution. While Helene takes the lead in the Dione-Helene dance, another moon, Polydeuces, trails behind, completing this celestial trio. Polydeuces, named after the twin brother of Helen of Troy, occupies the trailing Lagrange point in Dione's orbit, maintaining a fixed position behind its larger companion. Unlike Helene, which is relatively large and bright, Polydeuces is a faint and diminutive moon, only a few kilometers in diameter. Its small size makes it a challenging target for observation, and much about this distant dance companion remains shrouded in mystery. However, despite its diminutive stature, Polydeuces plays a role in the intricate gravitational ballet that governs the Dione system. The gravitational influence of Polydeuces, though subtle, contributes to the overall stability of the Dione-Helene-Polydeuces system. This three-body gravitational dance, governed by the laws of celestial mechanics, highlights the delicate balance of forces at play within planetary systems. Even seemingly insignificant objects, like Polydeuces, can exert a measurable influence on their surroundings, shaping the cosmic landscape over astronomical timescales. The gravitational dance between Dione, Helene, and Polydeuces is just one example of the intricate interplay of gravity that governs the movements of celestial bodies. Throughout Saturn's moon system, and indeed throughout the cosmos, moons and planets engage in a delicate ballet, their orbits intertwined in a complex web of gravitational resonances. These resonances occur when the orbital periods of two or more celestial bodies are related by a simple ratio, such as 1:2 or 2:3. When such a resonance exists, the gravitational tugs between the bodies occur at regular intervals, reinforcing certain orbital configurations and stabilizing the system over long periods. Dione, in addition to its relationship with Helene and Polydeuces, is also involved in other orbital resonances within the Saturnian system. For instance, its orbital period is nearly twice that of Enceladus, another intriguing moon of Saturn. This 2-to-1 resonance means that for every 2 orbits, Dione completes around Saturn, Enceladus completes 1. These resonances, like the rhythmic beats of a cosmic drum, influence the long-term evolution of these moons, contributing to their unique characteristics and histories. Dione Uncharted territory beckons. Cassini's mission transformed our understanding of Dione, but left us with more questions. Cassini's observations revealed hidden depths and intriguing possibilities. Imagine a future mission dedicated to unraveling Dione's secrets. Advanced instruments could map its subsurface ocean and search for hydrothermal activity. Such a mission could confirm the existence of this hidden realm. Imagine deploying landers to sample the subsurface ocean. This would be a monumental achievement in our quest to understand life beyond Earth. The tools for the task: envisioning future missions. Returning to Dione and plumbing its depths will require innovative spacecraft and instruments designed to withstand the harsh conditions of the outer solar system and address the specific scientific questions raised by this enigmatic moon. Fortunately, advances in spacecraft technology, coupled with the lessons learned from past missions like Cassini, have paved the way for even more ambitious explorations of the Saturnian system. One promising concept for a future Dione mission involves a spacecraft equipped with a powerful ice-penetrating radar. This radar would send radio waves through Dione's icy shell, bouncing back signals that could be used to create a detailed map of its subsurface ocean. By analyzing the reflected signals, scientists could determine the ocean's depth, salinity, and even detect potential hydrothermal vents on its floor. In addition to radar, a future Dione mission could employ a technique known as magnetometry to study the moon's internal structure. By measuring subtle variations in Dione's magnetic field, scientists could infer the presence of a subsurface ocean and potentially even map its currents and circulation patterns. Furthermore, a lander equipped with a seismometer could listen for Dionequakes, subtle vibrations in the moon's interior that could provide clues about its internal structure and the processes shaping its evolution. Exploring Dione pushes the boundaries of our understanding of planetary systems and the potential for life beyond Earth. Dione, with its subsurface ocean and geological activity, is a stepping stone to the outer solar system. Technologies developed for Dione could be applied to other icy moons like Europa and Enceladus. By exploring Dione, we pave the way for ambitious missions to other ocean worlds. As we conclude our exploration of Dione, we are left with a profound sense of awe and wonder. What was once a distant point of light has transformed into a world of captivating complexity. Dione, with its subsurface ocean and intriguing geological activity, stands as a beacon of scientific inquiry, inviting us to delve deeper into the mysteries of the outer solar system. Dione's story is a powerful reminder that our solar system is far from fully explored. The call of the cosmic unknown has always beckoned humanity, urging us to explore beyond the familiar confines of our home planet. Dione, with its alluring mysteries, stands as a compelling testament to the importance of such exploration. The prospect of returning to Dione, of delving into the secrets of its subsurface ocean, has never felt closer. The challenges are immense, requiring ingenuity and perseverance. Future missions will reveal more wonders hidden within this icy moon, captivating our imaginations. Dione's story is ultimately a story about us, about our innate human desire to explore, to understand, and to find our place in the grand scheme of the cosmos. It is a story that reminds us that we are part of something much larger than ourselves, a vast and interconnected universe teeming with wonder and possibility. By studying worlds like Dione, we gain a deeper appreciation for the fragility and preciousness of life, and we are inspired to become better stewards of our own planet. As we look to the future, the lessons learned from Dione and other celestial bodies will guide us as we venture further into space, establishing a permanent human presence on the Moon, sending astronauts to Mars, and exploring the outer solar system with ever-increasing ambition. Each new discovery, each tantalizing clue about the potential for life beyond Earth will fuel our collective imagination and propel us forward in our quest to unravel the mysteries of the universe. Dione's story is a testament to the power of human curiosity and our relentless pursuit of knowledge. It is a story that reminds us that the greatest discoveries are often those we least expect, found in the most unlikely of places. And it is a story that fills us with a sense of hope and wonder, reminding us that our journey of cosmic exploration has only just begun. The stars await, and Dione, with its secrets yet to be fully unveiled, beckons us to continue our exploration of the vast and awe-inspiring universe we call home.